I'm Sanjeev from ADS Department third year and I'm presenting my project XAI, an explainable AI deep learning framework for disease localization, chronic lung disease recognition system. In modern healthcare, deep learning models have achieved expert level accuracy in diagnosing disease from chest X-rays. However, they have faced a critical barrier, the black box problem. Doctors receive a prediction, but they don't know why the problem model made the decision. In a high-stakes medical environment, a probability score alone is insufficient. Clinicians need interpretability to trust the AI. My project addresses this by building a system that not only detects 14 distinct chronic lung diseases using ResNet50, but also visualizes the exact reasoning behind the diagnosis using Grad CAM and line algorithms. This turns the AI from a black box into a transparent second opinion for recog- radiologist. Now I'll explain my GitHub repository. This is my GitHub repo. Before demonstrating the execution, I want to walk you through the technical implementation and the modular structure of my code base hosted on my GitHub repository. The project is designed for modularity and scalability. Model.py. Model.py is this is this core backbone. I utilize ResNet50, a deep convolutional CNN network pre-trained on ImageNet. I modified the final fully connected layer to output 14 classes instead of the standard 10,000. Crucially, I used the sigmoid activation function instead of a softmax because lung disease are multi-label problems. A patient can have both pneumonia and edema simultaneously. Data loader.py. This module handles the NIH ChestX 14 dataset. It manages image preprocessing, resizing inputs 224 into 224 pixels and normalizing pixel intensity to match the ResNet50 requirements. It also handles data augmentation like rotations and flips to prevent overfitting. XAI utils.py. The script contains the logic for explainable AI. It implements the Grad CAM hook which intercepts the gradients at the final CNN layer to generate heat maps. It also contains the line implementation for super pixel segmentation. Run predict.bat. Finally, this batch script automates the inference pipeline, allowing for one-click execution that loads the weights and processes the input images. Live execution and demonstration we can see from our execution video. Now let's look at the system in action. Here you can see the project in environment in VS Code. We have a simple input image.png which is a raw chest X-ray exhibiting signs of image lung abnormally. To run the analysis, I execute run predict.bat script in the terminal. The system first initializes the environment and loads the trained PyTorch model weights onto the GPU for fast inference. Within seconds, the model outputs the prediction probabilities. As you can see in the terminal, the system has identified pneumothorax with a confidence score of 42%, followed by emphysema. Immediately after the prediction, the XAM model triggers the terminal logs generating GradCam and generating line. It is calculating that the gradients back through the network is to identify which pixels contributed to the pneumothorax prediction. The result is saved as sample output image is showed in this GitHub repo. In the center, the original X-ray image center GradCam. The heat map clearly highlights the specific region in the lung cavity. The red area indicates the high attention, confirming the model is looking at the collapsed lung tissue and not the background. The right is the line. The segmentation map defines the boundaries of the affected area. Methodology and algorithms. Let's briefly discuss the underlying of architecture diagram. Work. We chose ResNet50 because its skip connections solved the vanishing gradient problem, allowing us to train a 50-layer deep network efficiently. For the explainability layer, we used two distinct approaches, Grad CAM and Line. This both combinations ensures that the model is both accurate globally and interpretably locally. Phase 5 results and clinical impact. Our results were highly promising tested on the NIH dataset. The model achieved a mean first class accuracy of 93 and a mean accuracy of 0.86